So hi, a day later than planned, but this is the teardown of this cheap power supply that I bought in order to do some electroplating. Now on reflection I think I may well have bought the exact wrong thing, but let's take a look. So we've got a screwed up power supply, manual. Okay, yeah, I understand. No, I don't understand that. This power supply for high efficiency switching power supply, it has the load capability is strong, continuous working failure rate is low, good, and had a warm overload current limiting and various protective functions. Can be regulated to power supply, also used for current voltage regulator. So also used for current. Right, well, we'll see about all of that. That's impressively bad, isn't it? Let me get it out of the box. And yeah, pretty small and pretty light, I suppose, are my first impressions. So it's quite a neat little unit, made of metal, plastic front panel, of course, 3 LEDs. Straight up, I don't actually like this layout. I'd rather see positive, negative, and then earth on the outside. And the reason for that is that we use test connectors like this. The other thing, of course, that I note is that the ground connection is bright yellow, which is an interesting choice of colour. Let's have a quick look at the thing. So these actually come off, and these are obviously the cheapest you can buy. You can get these all over the place on eBay. Yeah, so the positive good piece of news is that this metal piece does have a flange at the back, which means you can kind of lay a piece of wire. I don't really have a piece of wire that's stripped, but yeah, you can lay a piece of wire into that and tighten up the nut on top. However, the nut does not repeat that flat piece of metal, so the contact is average. So display 3 digits, we've got an on-off button, a voltage control and a current control, which will be current limit. And yeah, actually that is a pot. I can just feel the end, but the knob is so loose that it just continues on indefinitely. The voltage, that's the end, is a little bit better. The knob grips a bit better. Feels like a multi-turn pot for that, so we'll find out. Yeah. Okay, let's plug it in. Okay, so that's not bad. In the back we do have obviously the normal socket. We've got a 222 to 110 volt switch, and we've got a fan which is not running at the moment. So maybe that is temperature controlled, or maybe it's just controlled by the current amount that we choose. Again, we'll find out in due course, no doubt. Okay. So we've got on and off. We don't actually turn the outputs on and off and have the device running. So that means there's no means to set the current limit. I mean, we can set the current limit, but we don't know what it's set to. So in the manual where it says you can use this as a current source, well, that has to be a pile of crap, because there's no way you can set the current correctly. The voltage is adjustable, that's fine. Does that mean I've got the, yeah, so, you know, there is no on-off switch at the output, so I've got 16.4 volts or whatever on the output now at 0 amps. So these are just 2 meters across the output. So 16.4, 16.41, so that's pretty good. Let's turn it up a lot. Yeah, 23.7, 23.72, so I'm happy with that. That's a perfectly acceptable voltage. Let's see how high we can go. 32 volts, 32.07. Can we go all the way down to 0? That's 2. That's 0.6, giving us 0.7 on there. 0.9, 0.1. Let's pick 1.2. Yeah, 1.25. 1.11. So you wouldn't want to be driving a precision FPGA circuit or something of this, because it's not precise enough, obviously. And given the price, yeah, it's not going to be. So that's all right. Let's put it under load. And I'm going to set it to just draw 0.1 amps. So Yeah, 0.09. So that's all right. So let's wind it up a bit to 0.5. So 0.5 amps, and apparently I'm drawing 0.499. So 0.49. So it's a place out. It should be showing 0. With rounding, this should be showing 0.5, but last digit being incorrect is pretty normal. Let's turn our voltage down there, so our current down, so it just limits. So what should happen is we should keep 0.99 here, and this should gradually decrease. No, it's just bottom straight out. So you can't use this as a current source. It's just not possible. So that part of the instruction manual is a complete lie. Okay, let's measure the voltage under load then. So let's turn our guy up a bit and draw 5 amps. Okay, so we're still delivering 13.6 volts here. On the load it's 13.3 because there's a bit of voltage drop in these cables, of course. And on the meter that's actually measuring the true output voltage, it's 13.39. So essentially this meter is no longer accurate. So we'll look at that when we tear it apart. I suspect what we're going to find is that they're not metering off the actual output. They're metering from some other part. But I suppose the point is it has, let's just suddenly turn that load off, and it appears that it has kept the regulation reasonably well. So in terms of voltage regulation, that's sort of all right. In terms of metering, that's not very clever. They've obviously not done the circuit correctly. So it should be a Kelvin connection onto the back of these actual sockets. Okay, anything else we want to do while this is in one piece? No, there isn't. I'm going to turn it off and tear it apart. That came off easily enough. And it's, you know, a reasonable gauge of metal. Walk over. So first thing I like to look at is the input mains. So this is metal boxed, enamelled metal, but there's plenty of exposed actual metal on the outside, and of course there's an exposed earth pin on this side. So just here is our earth connector. Now slightly bizarrely, yeah, you can see that that's got a blue wire soldered onto it. They haven't gone through the hole with that blue wire, they've just kind of soldered it onto the surface. And then over this side we have got our neutral. It should be neutral on that side. And then the live goes down to the fuse, and this back connection just here is the fuse, and they've just tag soldered this onto the front of each of those points. So I mean, you would expect, truthfully, you would expect to see a insulated crimp connector being pushed onto those, or this being fed physically through the hole, soldered, and then some heat shrink put over it. And really there should be a boot, plus rubber boot, placed right the way across the back of this connector to insulate it. So this doesn't meet the standards for double insulation, for example. The general principle is really simple. So you've got a mains connection here. So the requirement is, for safety purposes, that there should be a secondary mechanism that will protect the user should that type of thing happen. So normally we would do that by using crimp connectors that are insulated and things like that, and if it breaks off then actually there's no risk, and we'd have a boot around it so that if it came loose it doesn't actually come out, and we would put some physical cable restraints around it. Let's look at the earth. So we can see the blue earth wire, I mean blue really, the blue earth wire on the back here, and there it is, it goes straight onto the PCB just here, and again it's just tag soldered on the surface. That's actually a screw hole it's been attached to. There's no screw in there, and they haven't even fed it through the hole, and it's not going to the case. There's only one wire coming off that earth pin, and this is it. It's going to a track on the PCB, and the track runs along the bottom. Yeah, so the track runs along the bottom of the board. It is solder masked, so it has got insulation over the front of it, and pops up to this screw hole just here, and a yellow and green cable comes off and goes straight to the front panel. Now strangely, they've decided that they're going to heat shrink that one. Now the front panel is fully plastic. There is no electrical connection between the front panel and the body. So far I haven't actually found an earth connection that is going to the chassis at all. So this bottom section here is all of our mains input and first switching regulator. So I'm not really seeing anything interesting on that. I've got no Y caps running off that. So I've got some suppression caps up here. This is another rail running along, and that is that's physically connected with a couple of screws to the chassis. But how the earth actually gets up to it is anyone's guess. Let's have a quick continuity reading on the actual earth to case. Let me see if I can get my fingers out of the way so you can kind of see where it is. So this is the switch for the power selection. 54 ohms. What about this guy up here? 0.125. Yeah, so there's a very, very dodgy connection through to earth. I'm going to plug this into a pat tester and just see if it even passes a pat test. Okay, hopefully you guys can see what's going on here. So cover, yeah, that was all right. Power cord was all right, I think. Plug was pass, okay. So we're ready for our earthing test. Oops, we've failed straight away. Okay, so yeah, so this does not meet any European standard anywhere. Oh damn, got the wrong test selected. Okay, so correct test selected. So it's showing that I need to plug in my two plugs into the relevant spaces, so I have done that. It's running a 25 amp test on the earth cable, which is measuring at 0.04 ohms, so that's a pass. Here we go, high voltage test. Also pass, excellent. Low voltage test. Good. Okay, so that's excellent. The cable actually does pass, the device does not. Before I explore the circuit, just a few thoughts on that then. So I bought this from a UK reseller. So I'm going to be honest, this is illegal for sale in the UK. You may not sell it in this state for very good reasons. It's not properly earthed, and the connections through on this socket here are, you know, flapping in the breeze. If we turn it over and we follow them through, yeah, they're these connections here. These are your mains connections down here, and they've literally just held them on the back of the board and applied a blob of solder. So there's no strain release, there's nothing. Vibration, anything can just cause that to snap off and come off against the case, and that's your live to the case. These all relate to voltage switching and go out to the mains switch. So I'm not sure that that's actually switching the true mains or whether it's actually switching the switch mode power supply, but either way they're connected just the same, just soldered, tag soldered onto the back, and that is an absolutely unacceptable way to be. I mean, it's an unacceptable way to be connecting anything to your circuit board, just flapping around loose connections. It's particularly unacceptable for your main high voltage lines and they're high current lines. So there's nothing delicate about these. these are killing voltages and currents on all of these wires that are just lightly tagged on the back with absolutely nothing to stop you to stop them coming off and contacting the case. The case itself is not properly earthed. So, you know, this is essentially a dangerous piece of equipment. It needs some work. If I decide to use it for anything, I will have to do several upgrades, and it's not really difficult to do. So there's absolutely no reason for doing this at all. The full facility is on the board to enable proper connectors to be put on and to actually do proper crimped or soldered, if you wish, connections, either way, but to actually do a proper job of them. You know, we go over to the low voltage stuff and it's got connectors. You know, the high voltage stuff should have connectors, better ones than that, but you know, there we go. Anyway, rant over. Let's look at how this this circuit sort of works. So I'm not going to be able to look at everything, obviously, but let's follow it through and just see if we can see the main route. So the mains actually comes in down here. Now, that looks then like that is like these two capacitors would be that we would have a bridge rectifier and then these two capacitors for the start, but that isn't the case. They don't actually belong to that mains connection. These are only 200 volts, so so that's not them. They're for a different stage, which we'll come back to. But along here we have a classic. So we've got some X capacitors here. We've got a choke just here. We've got another X capacitor here. We've got a MOV down here for a bit of input protection. Obviously, there's a fuse. So I'm kind of all right with that. That's okay. And we have a little bit of slotting in the board down here to create a bit of separation, and we've got a capacitor across it. That's okay, that's fine, that'll be to the ground, that's super. And then we've got a transformer between the high and the low voltage sides, which is normal, and that's crossing the slot, so that's all good. And then down here we have got our this will be our controller IC, this will be our switch mode IC, and I think looking at this, it will just be giving a fixed voltage, maybe 30 odd volts or something. I don't really know the voltage, but it's going to be giving a fixed voltage. Now, generally speaking, what you'd expect to have there is a rectifier diode, which is just here, and yeah, some high voltage capacitors, which are just here. These are 400 volt capacitors, no names, of course, but and that will be feeding into this, and this will be a kind of self-contained IC, and it will use an optocoupler to feed back the voltage, and the optocoupler is right here. So this is a bog standard circuit, really. You know, the only thing that I don't like is that this slot, why doesn't this slot go under the optocoupler? So I noticed that there are 4 pins on the side of this IC that are joined together, which means it must be have the switching transistor and everything inside it. So I think this is just a drop-in simple component. Let's have a look at its part number if we can. Oh, there you go, it's a TNY280. So yeah, so I do recognise that. That is a simple high to low volt switch mode controller. Let me leave it propped up on something so that okay, and here it is. So a TNY274 to 280 series. It's a tiny switch series from Power Integration. It is a lowest system cost on-off line switcher with enhanced flexibility and power range. So basically, it's a switch mode power supply controller, and we can see the diagram on the right hand side. So we've got our positive DC coming in to the top of a transformer, a diode going back as you would expect, and this device sitting between the bottom of that transformer and ground. So it's essentially switching the current on and off in that transformer very, very rapidly. I don't know if it says what the frequency is somewhere, and and it's using a feedback. For feedback, it's using this what's the word I'm looking for? Optocoupler. on the low voltage side, which has also just got a simple regulation, a bit of Zener to set the range for the feedback. And yeah, that's your lot really. What's it sort of, yeah, so yeah, we're looking at 20 watts, something like that. So it's obviously not the main supply. So that's the whole of this side really dealt with. If we look a little bit further along, we can see a few more ICs. So just here, can I see the part number on that? Okay, that's an SG 3525. So an SG 3525 is, let me just think about this. Yeah, it's a pulse width modulator. So this isn't a full switching thing on its own, but you would use it within it's designed for use within a switch mode power supply. So this is on your DC to DC converter for the high current, low voltage side of things. So this is your 0 to 30 volt voltage control really. So it's pulse width modulation controller, and then round it there will be a few op amps without a doubt. Yeah, so one just here, which is a TL084 classic 4 op amps on one package, and another one up here which is a 2904. Yeah, so again another classic op amp just there. So they will essentially just be monitoring the voltage against the set point, and monitoring the current also against the set point. So yeah, there's the current shunt. So essentially we've got on this side, we've got our single voltage regulation creating low voltage. That'll be powering all of the circuitry around here, and also the circuits that are in the front cover for the meters. And then we've got another route coming through with a different switch mode power supply, actually doing the high current side. Yeah, interesting, there's a bit of cardboard underneath the coil here, just flapping around. It's coming loose. In fact, the coil is also rather loose. It just needs a bit of Celastic or hot glue or something on there. Same with these big capacitors, they should be glued as well. But anyway, yeah, so we go through there, then we got another circuit here which is providing a different form of switch mode with the higher current. See the big transformer there, another transformer here, and yeah, and a couple of pots to actually trim in the range a little bit. So nothing very much very exciting happening there. So we've got two switch mode type things going on. One is your high voltage side, the other as a including these big capacitors here as the low voltage high current side. And yeah, and these will be the two pass transistors, presumably in parallel, to provide the 5 amps. And then they just put bigger heat sinks on if you want more current. Fantastic. And possibly another capacitor in this empty space, I'm guessing. But that's it. That's all she wrote. If we have a look inside the front panel, we can see a circuit board which has two very similar circuits on it. I can't unfortunately see the part number here. The conformal coating is in the way, but we've got as well as the 76E003 AT20, I think. There you go. So they've literally popped a microcontroller in there, and they're using the ADC to read the value and drive the display. The current one, sorry, that's the, which one is that? That's the current one, sorry. The current one comes back to here, which is right next to the current shunt. So it might be the microcontroller might have some embedded embedded op amps or something on like that, because normally you would need an op amp to amplify up the value. Okay, so what I think I'm going to do with this, I mean, I might just give it a go and see if I can persuade it to provide appropriate current for my electroplating attempt. But once I've done that, I reckon that there might be enough space in this to make a modification. So what I'm thinking of doing is turning this into a constant current supply, or regulated current supply, variable current supply, that would be a better way of putting it. So sorry for switching to dubbing over this, but the microphone gave up the ghost about 30 seconds in, and what we're going to do, I think, is build a little board which will add a voltage limiter. Instead of this being a variable voltage supply, it will become a voltage limited supply, and a current regulator. Now most of the circuitry is already present. We've got current monitoring, we've got current limit setting, we've got voltage setting. So pretty much everything we want is already on the board. We're probably just going to need 3 or 4 op amps to enable us to control current instead of voltage. The other thing I'm going to do is put a switch on the output so that I can switch the outputs off, and then instead of only metering the output voltage and current, it will enable us to see on the display what the set points are as well. So that's the plan. That'll be a separate video, see how that goes. So anyway, in the meantime, please remember to subscribe, to thumbs up, like the video, and of course to leave comments down below. See you next time. Take care.